F322 Jan 13, question 2. Apologies to those following these questions from question 1. I think my memory ran out or something, so I got halfway through this question 2. I'm going to take it from the top again. Phosphoric acid being manufactured, two-step process. We're looking at delta H1, the top equation here, and A is asking you, delta H1, does it represent the enthalpy change of formation of P4O10? This is a roundabout way. You've got the answer there, unfortunately for you already. This is a roundabout way of asking a definition for enthalpy of formation. So, if you can remember your definition, you're going to look and see here, have I got 1 mole? Yes. Now, enthalpy of formation, big hint in the fact that it's something formation, forming, being made. We're making 1 mole of a compound from its elements. So, check, have we got the elements there? We do. So, the answer to this question is essentially the definition for the enthalpy for delta H, the enthalpy change of formation definition, but it's very, very specific. So it's the enthalpy change to form 1 mole of P4O10 from its elements. Then part B wants you to actually do a calculation. So enthalpy changes of formation are shown in the table. Here we've got our table. It's given you formation data. So if you're going to try and draw your cycle, you want to start, and I apologise for the scruffiness of that equation, you want to start with the top equation of for delta H2 that you've got there, so P4O10 plus 6 water will give you the enthalpy change delta H2 and produce 4 phosphoric acid. Because it's given us formation data at the bottom of our cycle, we're forming from our elements. So at the bottom of your cycle, you've got your elements. And here I just want to do a little bit of adjustment because I want to make clear that these arrows here are going in the opposite direction. They're different. So these two arrows aside for a moment, we've got our elements at the bottom, we've got forming P4O10 from its elements, so the arrow is going upwards. We've got forming water from its elements, so the arrow going upwards, and we've got forming of phosphoric acid from all our elements going upwards. You've got the data that's been put in there for each of them. Notice if it's 4 moles of phosphoric acid, I'm timesing by 4 because my data is for the formation of 1 mole, and here I've got 4 moles, so I'm timesing by 4. Now, to actually write this in, I've got to do some sign changing because I want to get from here to there. I want to work out what my delta H2 value is, which is this enthalpy change here. To do that, I want to travel around the cycle this way. So I'm changing the direction of my arrows here and here, and so ultimately that means I'm changing the sign. So here I've got my delta H2 is equal to plus 2984 plus, I put in brackets here, 286 times 6, but then plus again, but this time plus is minus 1267 times 4, and that should all equal minus 368, and that is your final answer. you get 1 mark for correctly working out what the enthalpy change with the right signs for your reactants is, and 1 mark for correctly calculating your products. And then your final mark, obviously, for the answer. You get 3 marks if that answer is correct, whatever you're working. So here, done the cycle, change the arrows, importantly, change the signs, times by the number of moles. Here, because I'm adding generally all the time, I've changed this sign from minus, I've changed that sign from minus, that one stays the same. And I get my answer of minus 368, and it's given me the answer, my units, kilojoules per mole, to the minus 1. Now, in this final question, quite a nasty one, this one. Write the overall equation for the manufacture of phosphoric acid from P4. So we've got to go back up to our 2 equations, and we've got to use our cancelling out skills from our radical substitution. Because here, if you look at what you've got P4 plus oxygen gives P4O10, and then you've got your P4O10 in the next equation plus water giving you your phosphoric acid. So what you can do to work out what this overall equation is cancel out these 2 P4O10s, and then your overall equation is simply what's left on this side. P4 5O2 6H2O is going to give me my phosphoric acid. So the trick here is just to cancel these 2 out and then write it as a full equation. So back to the question, if I could remember actually what I've just said, you should have, still rising, aren't I, P4 plus your oxygens, which I think was 5O2, plus your 6 waters, that's what it was, and that goes to your 4 phosphoric acids. So all you've done is from those 2 equations is cancel out what was on the left and right hand side, the P4O10. You can't get this next mark to explain why the process is 100% atom economy if you've not got the correct equation. So it's quite harsh here. If you miss that equation, you miss all the marks in this question. What you want to say, 100% atom economy, therefore key thing for atom economy, no waste. That's really what you want to put. We've got a single desired product with no waste. So I think I'm just going to put in here there are no waste products. Crucially, you cannot just say there is only one product. That will not get you the mark. You need, because it's atom economy, you need to make sure you're saying keywords, no waste products. F322 Jan 13, question 3. Organic chemistry now. So, pentan 2-ol can be converted into 3 alkanes, A, B, and C, by the elimination of water. 2 of the alkenes, A and B, are stereoisomers. The 3rd alkene, C, is a structural isomer of A and B. So, clicking on, you should be aware, key word here, alkenes. Pentan 2-ol, an alkylol, is going to be converted into an alkene. So immediately you should be thinking, it's told you it's elimination, you've got loss of water. Now it's saying that you can get 3 products from it, but then it's giving you this key word, stereoisomers. What sort of isomers do you know that are stereoisomers? EZ. So we're going to have one isomer with or one structural formula with EZ isomers, and we're going to have third alkene C, which isn't going to make EZ isomers. But we'll come to that because we've got a few questions to answer before we even get to trying to draw out these products. So first of all, what is a suitable catalyst for this reaction? You just want to say an acid catalyst, and here I've got, what have I got there? H2SO2. You have to excuse me for that there. It's going to be H2SO4, of course. Then, next, key thing to look at here, molecular formula. It's put it there. So many people lose a mark here. Construct an equation using molecular formula for the elimination of water from pentan-2-ol. So C5H12O. Don't be tempted to put that OH at the end. Gives you lost the water, H2O, C5H10. It's here that people make that mistake because they've not seen molecular formula, and you will not get the mark even though you've got the right equation because they've asked for molecular formula. Then going down, explain what is meant by stereoisomers and structural isomers. So structural isomers, they're going to have the same molecular formula but different structural formula. I should put really formulae there to be fair. I think, yeah, it's going to let me do it. Okay, then stereoisomers, they're going to have, and in fact these two, they sort of follow on. Structural isomers, same molecular formula, different structural formulae. Stereoisomers, different structural formula, but then you have your different arrangement of atoms in space. So stereoisomers, same structural formula, different arrangement of atoms. Now, over the page, we've got to then go and try and draw out our stereoisomers. So here we've got A and B to draw. Let's just draw what we've got at the top, just so we know what we're talking about. We've got pentan-2-ol, haven't we? So C, 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 with an OH there. Now, what's going to happen here, we're going to lose that OH, and we're going to lose an H from either here or here, depending on the type of isomer I'm going to form. Now, if I'm going to form stereoisomers, can I lose a hydrogen from here? I've got my 3 hydrogens on here. If I lose one of those hydrogens, I've got a hydrogen there and a hydrogen here. Will that give me a stereoisomer? No, it won't, will it? Because I've got 2 H's, and I need, for a stereoisomer, for an EZ isomer, I need 2 different groups. So that's not going to be stereoisomer A or B. That's going to be my structure C, where the double bond comes in here. My OH here, then, I'm going to lose this H, and I'm going to get my double bond here. So, placing my double bond in the middle, I've lost my OH off here, and I'm left with a CH3. Shift off. I can see this is going to be fun drawing this. Hold on a second. Okay, having some small problems with my pen, but now, unfortunately, it's a bit scruffy. But what we can see, if we're going to draw these structural isomers A and B, I'm going to use the red circle for A and B, and I'm going to take off the OH and the H from carbons 2 and 3. That will leave me with a methyl group and a hydrogen on this first carbon, and on this carbon here I'll be left with a hydrogen and an ethyl group, that is C2H5, which will allow me to have these 2 isomers A and B. Here I've got the 2 H's on the same side, so this is cis, they're on the same side, So this is my Z cis isomer, and here I've got my trans E isomer because we're going across, they're going diagonally. My final isomer C then is taking the water from this green circle, and so I'm left with a carbon at the end with only two H's. So same groups, two H's, it won't form a stereoisomer, and we get then this final isomer C, which is pent 1-ene. Notice here in the mark scheme, they wanted you specifically to show them that this was a straight chain of CH2, CH2, CH3. You would not have got the mark for doing a molecular formula abbreviation here of C3H7, because within that C3H7 you could have placed a methyl group. So they wanted to see that that was a straight chain. So be cautious about your abbreviations. Just above here, C2H5 is fine because you can't have anything but that ethyl group, which is two C's in a row. But when you get down to more than two C's, three C's or above, there's possibilities of branching. It wants you to demonstrate that you've got the straight chain, because your initial isomer with pentam 2-ol, which was a straight chain. Then on, since you've drawn out your EZ isomerism, they now want you to be able to state what features it has. And these are these two features. The first being that they contain a carbon-to-carbon double bond that restricts rotation. Key there, it's not just a double bond, it's a carbon-to-carbon double bond. And then the second point is that each C of the CC double bond has two different groups attached, and that again is the point that a lot of people miss, that it's each C of the CC bond that has two different groups. It's not just a carbon with two different groups attached, because it could be any old carbon in the chain. It's very important that you put that each C of the CC has two different groups. Then the question goes on to ask, if it's oxidized, can you write me an equation for it? Notice here that they want you to use skeletal formula for the organic product. So you don't have to put water in a skeletal formula, because that's not an organic product, because it doesn't have carbon. So we've got for our formula here, it's a secondary alcohol. So with 1O in square brackets, we produce a ketone plus water. Notice the way we've done that. 1, 2, 3, 4, 5 carbons. The H is coming off here, and it's being replaced by a double bond O. You've actually got two H's that come off, one from here that you can't see in the skeletal formula, to produce the water with your O in square brackets, and you produce a ketone. Secondary alcohols, 1O in square brackets, ketone plus water. Then moving on, they want to test your knowledge of different reaction conditions for oxidation. So they've given you this time pent 1-ol, so a primary alcohol that can be can react to form different things under distillation and under reflux. Here you've got the aldehyde formed under distillation and the carboxylic acid formed under reflux. It's vitally important that you learn these oxidation reactions, because they do come up in each paper.